Okay, this is week 6, and we are doing lab 4 for this week. And as you know, there's a lab submission for this week. Without further ado, let me share the slides, and we shall discuss on the lab submission and as the lab content as well. Now, let me first adjust the volume so that you can hear the sound, and as well as the I will hide the floating meeting control so that it will not block the screen. Now let me put it to the slideshow mode. Okay, for Lab 4, as you know, it is the introduction to signal conditioning and sampling, and it happenings on week 6, week 6, which is this week. So basically, inside Lab 4 folder, you will be able to find the detailed lab sheet, which is the whole write-up of the whole lab procedure. So you should use this as a main copy to follow your steps, right? Now, there is also a video, Lab 4 video, PowerPoint appended. This is for additional video for you to view if you would like additional information about LabVIEW related to this chapter, this lab. And then also this slides, which is Lab 4, will be placed into the Zoom. Later, I'll rename it into Lab 4 slides instead of Lab 4 Zoom. So you will use this as a Lab 4 slides. Now, for submission, let's say if you are in N1 group, basically you would use this link, N1 Lab 4 section 1 and 2 submission. So basically, in this Lab 4, there is actually total of 3 sections, section 1, 2, and 3. But for all of you, the submission is only on section 1 and section 2. Basically, when you submit, you just need to click this link. So what I need you to submit is for the section 1 and 2, you need to do all the observation. And after writing down all your observation in these pages, then you can use a cam scanner to scan the multi-page into a multi-page PDF, not single PDF page. So you have multi-page into one document. And then name this document as name admin.pdf, right? Okay, you can write or type your name at the top right-hand corner of each page before scanning. You can submit the PDF document via the Blackboard by clicking this link with, above. This is not just a title, this is also a link. And then, of course, the submission date for this this particular lab submission is 28th of May, which is the last day at 6 p.m. Now, anyone or more person caught with the similarity of more than 80%, marks will be deducted. So you can discuss. I don't deny the fact, but please do not copy wholesale. Right? So if you don't have more than 80%, I will close one eyes. But then if you have more than 80%, marks will be deducted. And this will not be communicated to you. I will just deduct accordingly. Now, submission later than the deadline. So if you submit later at deadline, again, marks will be prorated. Okay, marks will be prorated. So instead, let's say you submit 1 day later, people get 100% of their mark. You will get maybe around 90% for first day, maybe 80% for second day, etc., etc. So 80% of the mark that you're supposed to score. So let's say the total mark that you for your submission is only 60, then you will multiply by 0.8. Let's say you are 2 days late, so it's multiplied by 0.8. So that's how it goes. So this is to be fair for people who is on time, rather than you know, we don't. We don't want the people to be on time to be like, hey, I'm doing it for nothing's sake, because the rest that is late also get the same mark as me, right? So in order to be fair, we do it this way. Now, for Lab 4, basically, like what I say is signal conditioning sampling, and it's a lab submission. Basically, we are doing section 1 and 2, right? Now, of course, section 1 and 2, the section 1 is signal conditioning, which is page 4 to page 5 of your document, of your detailed document. It contains the observation section. That means A, B, C, D, E, right? So you need to answer this A, B, C, D, E portion for your section 1. And section 2 is only A, B, C. So it's page 8 and page 9. So these 2 pages. Of course, these 2 are with the asterisk. So therefore, the submission is on these 2 pages. Now, the star is slightly offsetted. So maybe, but of course, section 3, you don't have to submit. So basically, we only submit section 1 and 2. Let me correct the star, because it's too far out. Just in case you guys are confused. Now let me continue sharing again. Now, so this should be the case. So you are supposed to submit section 1 A to E, the observation, and section 2, the observation A to C. Now, section 3, there is no need to submit, but section 3 is there. So I will be demonstrating to you for section 3. So submit the observation for those marked with asterisk star. So basically this one and this one. Okay. Now, let's go through a little bit of theory on the signal conditioning filtering. Now, filtering, as we know, when we have a signal and a noise mixed together, you have a noisy signal, right? So that is basically looking at the time domain. If you try to eliminate the noise from the signal in a time domain, it looks very, very difficult. So it's almost like impossible. It's like telling you to mix a can of red beans and a can of green beans and pour them together into a big pail and then stir it and mix. Now, the next moment I tell you to pick out the red beans from the green beans, it is a very tedious job. Likewise, this is going to be a very tedious job to separate the sine wave from the noise, right? So therefore, if we just look at the time domain, it is impossible, right? But of course, if we look at the frequency domain, which I'm going to share in the next page, you realize that the noise for the previous page, the noise is circulating at a very high frequency. So basically, the noise in that page will appear higher noise, and then the signal will be lower, right? So for that particular one, and of course in the frequency domain, you can see that they are quite spaced out. So that means the signal and noise can be clearly distinguished, right? If you look at the frequency domain for the high frequency noise and low frequency signal. So with this, we can actually use a low pass filter. Low pass filter will suppress the high frequency after it's cut off frequency. So you suppress everything, so meaning that the noise will be suppressed away and it will pass the signal frequency. So this is to use a low pass filter, right? With high frequency noise. Now, of course, there is a situation whereby you have low frequency noise, like the power supply noise that is 50 hertz. Now, this is the kind of low frequency noise, whereas the signal is at a higher frequency. So, of course, the shape will not be exactly like what I demonstrated to you the previous page. But note that, again, in the frequency domain, you can see that the noise will be quite distinctly separated from the signal. Now, with this situation, when the noise is lower frequency as compared to the signal, we use a high pass filter. Now, high pass filter will suppress those signal before it's cut off. So meaning that noise 1 will be suppressed or will be eliminated. And whereas the signal, which is after the cut off and which is the pass band, within the pass band will be passed. So likewise, this guy you can use to suppress noise that is lower frequency than the signal. Now, if the noise happens at both the low frequency side and the high frequency side, and the signal is just happen to be in between them, then what you can do is to use a band pass filter. Now, band pass filter can be constructed from a low pass filter as denoted by the red color, and a high pass filter as denoted by the green color, and joined together. So when you join both together, it form a band pass filter. So meaning that it only pass the band between, say, 1K to 20K. Now, other than that, the rest of them is the stop band. So noise 1 and noise 2 will be also eliminated under this case, right? So for section 1 in the lab sheet, which is signal conditioning, you are supposed to have this front panel, and this is figure 4.1, right? Figure 4.1. And of course, also for the block diagram, you are supposed to wire up this particular connection here. We denote it as 4.2. Now, just take a look at this setup. Basically, for this part here, with offset frequency and amplitude and sine waveform, this is to define the sine wave. What is its amplitude, its frequency, and its offset to be injected into the signal. Of course, we are using virtual simulation, so therefore we have blocks in this lab view to define all these things for the sine wave, right? Now, of course, again, this noise is also artificially injected by a certain model, the Gaussian white noise model. And of course, in the input, we have to define the standard deviation and the seed and the seed will be the amplitude for the noise, right? Now, if you sum both of them together, which is what we've seen in the diagram, you sum the sine wave with the noise, then what happens here in the simulated signal, you should get a noisy signal. Now, also arbitrarily, we also detect using a DC average to detect the DC signal of the outcoming signal. And then after that, we do a subtract, basically to remove the DC component from the signal. And after that, you do, right, by doing a DC subtract here, right, signal. So after the signal subtract, we monitor again, and you can see the signal without the DC offset. Now, after this, we pump the signal into a low-pass filter. This is also constructed by the model in LabVIEW. And of course, the parameter that we define for the low-pass filter is the low cutoff frequency, right? With this, after injecting in the low-pass filter, you can see that after suppressing, of course, you must define the cutoff frequency properly so that you clearly can separate between the noise and the signal. If you don't do it carefully, sometimes both your signal and noise can be suppressed, or both your signal and noise can be passed. So therefore, this definition of the low cutoff frequency is very important, right? So this is for section 1. Now, going ahead, of course, I need you to submit observation for A to E for section 1. Of course, it looks something like that. This is for part A. I'm demonstrating to you the part A, how to do it. So once you wire up your VI, front panel and back view, and basically you need to key in the condition. So first step is to fill up the condition of observation A. So you just fill in the frequency, 10 Hertz here, amplitude 1 volt here, and then of course DC offset is 0 volt, you put it here. Then for the noise, you have 0 amplitude, and of course standard deviation also is 0, so you put it down here. Then also for the DC offset here, you put 0 because it's defined as 0, and then of course the cutoff frequency is 10. Now, please ignore this diagram first. Later I will explain why there is an additional block. You notice that in your previous one there is only 3 graphs, right? But for this case, I am demonstrating to you using a 4 graph situation. I'll explain to you why. Now, once you fill up all these parameters in the box, we will click run, right? Click run. Now, once you click run, you realize that of course, again, ignoring this one, this is for figure 4.4 and 4.5, which is for section 2. You don't need it down. In fact, section 1 and section 2 is pretty much the same. It's just that this additional graph that is different. So what I'm using now, what I'm doing now is basically using section 2 block diagram and front panel for section 1 simulation also. So we can do so because that will save time. If you do section 1 block diagram, then section 2 block diagram, then you still have to modify your section 1 block diagram to section 2 in order to do section 2. So might as well we start off with section 2 block diagram and the front panel, and then we can capture the result for section 1 and section 2 together using the same block diagram. So that's what I mean. Now, once you click the run, basically you'll be able to see that the signal result is shown here. Now, so step 3 is to observe your result, right? Now, so for the first one, it says that simulated signal. So you look at the simulated signal graph, it's a sine wave, so of a 1 volt peak to peak. So you say plus minus 1 volt peak to peak, that's your observation. It's a 10 Hertz sine wave because you define it as 10 Hertz, right? So this is your 10 Hertz sine wave. Now, after that, you look at the after offset remover, which is after offset remover. Since the offset of this guy is 0 and then remover is also 0, so there is actually no offset different, right? So therefore, this is actually identical of that. So therefore, it is again is 1 volt peak to peak, 10 Hertz sine wave. So my observation is just that. Now, after the third one, which is the after filtering. After filtering, you notice some difference. Originally, your peak to peak is at 1 volt peak, plus minus 1 volt peak to peak. Now, after the filtering, you realize it dropped to 0.707 peak to plus minus 0.07, 0707 peak to peak. And of course, it's still a 10 Hertz sine wave, right? Now, so the deduction here is because the signal frequencies sit at exactly the cutoff. And we know that the cutoff is actually minus 3 dB now. It's not 0 dB. So because minus 3 dB, it will be, the whole strength will be divided by √2. So you take 1 divided by √2 is actually 0.707. So therefore, the amplitude went from 1 volt to 0.707. So this is for part A. Of course, part A, in order to demonstrate to you, I give you the solution as well. So you can write down the same part A solution, right? You can do it the same manner as I do it, or you can do it other way. I leave it free of choice. There is no standard rule, but this is what I kind of expect, right? So then, of course, moving ahead, we will continue with the theory for part 2. Now, part 2, we talk about ADC, sample and hold. As you already know, we need to sample because we need to limit the memory involved. If you start to store the entire analog signal, which is infinite signal, then you need infinite memory space, which is not enough for any computer that is existing today, right? So as a result, you need to take samples. And because of the taking of samples, you are then limiting the analog signal in time domain. So that means your time duration gets shorter to about TS, right? The TS is between two signals. So because of your time limit to TS, your frequency domain suddenly from one original signal spectrum is spread out to multiple spectrum based centering around the sampling frequency, multiple of the sampling frequency. So each of the multiple of sampling frequency, you'll see one identical original spectrum that is recreated here. And of course, in the negative side. So this is what we call, these are what we call image spectrum due to the sampling. Now, this is the original spectrum. If you have the, you have not do the sampling, it is just the original spectrum itself. But once you sample, it will recreate the image spectrum because of the sampling, because of this frequency is 1 over time kind of relationship, which I have explained in the lecture, right? So what happens is next, of course, we mentioned before, or if this is the first time you're hearing it, then we say that if you do not sample enough, so basically you just sample 5 point in this particular signal. Now, 5 point in this particular signal, of course, the original signal is still centering in the 0, but because your sampling frequency, which is the Fs or omega s, is not huge enough, so therefore the spacing between each of the image spectrum and the original spectrum is very close together. So as a result, they overlap each other. And this overlapping is what we call the aliasing, right? Aliasing due to sampling not enough. So when you have sampling not enough, in frequency domain is an overlapping of the spectrum. But in the time domain, if you join the dots, basically you can never recover the sine wave anymore, because this is basically look more like a triangular wave than a sine wave. So this is a situation if you do not sample enough. So if your sampling frequency is too low, right, aliasing occur, information are lost. So that's the reason. Now, if I sample a lot by being very kiasu, so I sample a lot of points, again, it defeats the purpose. Why? Because you can recreate the signal, yes, but then your memory will be full. Of course, there will not be aliasing because you are sampling very close together, and in the time domain it is very close together. In the frequency domain is very fast spaced out, so there's no chance that this can the frequency spectrum can overlap. So as a result, we don't worry about the aliasing problem in a very high frequency sampling. But this will also result in memory full very easily. So this is a no-no, because this is just a one tone sine wave. You use so much memory for one tone sine wave, it doesn't make sense, right? Now, so if we were to sample at a Nyquist Shannon is the guy that noticed this and then recommended this sampling rate. He says that if you can sample and if you know the maximum frequency of your signal, sometimes your signal is not just one frequency, it can be a group of frequency, and you take the maximum frequency, we call it Fmax, and you multiply that Fmax by 2. So as long as you sample the sample point at a rate which is greater than 2 Fmax, then you are okay. You can recover most of the signal without distortion. That's what Shannon Nyquist recommends. So basically, it works. So that's why people after that do sample and hold and for ADC all follows Nyquist's recommendation, and that's the theory that has been legacy from the day that he noticed this, and of course maybe he put it in the mentioned disclosure. Until today, everybody is following his Shannon-Nyquist theorem, right? So if you sample in the correct time, basically you get the time domain signal not distorted and the frequency spectrum not overlapping. So that's the best ideal case. And then of course you save on the memory. So for the section 2, as I mentioned before, we add in another graph, which we have the filter and sample signal. Now, so basically in the front panel, the only difference is one more graph. So therefore, that's why just now I started off with 4.4 instead of 4.4. The previous two block diagram and block diagram and the front panel, right? So I basically straight away come to 4.4 and start to wire it. So you can do the same thing, because only the section 2 block diagram and front panel need to be submitted, but the front one, the section 1 block diagram and front panel, no need to be submitted. So what you can do is you can wire figure 4.4 and 4.5 and use that for your section 1 collection of data, which you can do so, and then also use the same block diagram and front panel for section 2 collection. So basically you only need to wire one of them, right, which is figure 4.4 and 4.5. So the additional thing is also here, we add in additional sample and hold circuitry to do the sample and hold, and of course we change the auto detect DC offset to a DC offset signal here. So that's basically the difference between the first block diagram and this section 2 block diagram. So basically I will start off with this, that's easier. Okay. Now again, for section 2, there's only ABC, right? ABC. So again, I need you to fill up the condition after observation. So basically, same thing. You just need to key in all the parameters. So first of one, you fill up all the parameters here, as indicated by the arrows, and then you click run. So once you do that, the step 3 is to observe, yeah? Observe the signal. So of course you see very noisy signal here, there, then you get very nervous. But look at what the observation wants you to observe. So basically they want you to observe the sampled signal. So if you look at there is a sampled signal, there's a filtered signal. So you just look at the sampled signal, which is the red color here. So it's not really a sine wave, right? Because we started off as sine wave here by keying in a sine wave of frequency 20 Hertz. But it's not really a sine wave here, it's actually very distorted. So we call this a distorted signal, and aliasing have occurred, right? So if you ask me about frequency spectrum, probably, yeah, because aliasing have occurred, probably the original spectrum and the side spectrum has overlapped, and this is what we call aliasing, right? So this is the for section A. Section 2, question A. But of course, B and C, you have to do it yourself. I just guide you for the part 1. Part A. Next, we move on to ADC, which is sample and hold, and this is primarily for the theory for section 3. Yeah. So all the quantization level involved needs to be round off to the nearest level, therefore resulting in quantization error. Now, as we know, ADC will be coding the quantization will be coding from its lowest value to the highest value. Now, so if you put the lowest value as 0 volt and say the highest value as 1 volt, then the rest of the level, which is from 000 to 001, 010, all the way up to 111, each will be equally spaced out, right? Equally spaced out. And but because this is equally spaced out, the sampled signal, the whole signal, may not exactly coincide with this level. So as a result, depending on whether you are using a 0.5 VLSB quantization rule or you are using a full VLSB quantization rule, which we went through in the tutorial. For 0.5 VLSB, you can either resolve to the nearest higher level or resolve to the nearest lower level, depending on which one is nearer. Right? That's for half VLSB. But for full VLSB, no matter what, as long as you never touch the next higher level, you always resolve down. And that's why it's called a full VLSB. Now, we also mentioned that as long as you use 2 to the power of 3 or 8, then there will be actually 7 interval, because 8 level, then the interval between it will be 7, right? And because of this, when you resolve it, the error is as per what has shown. Now, if you increase the number of bits, say to 4 bits now, then 4 bits will result in 16 level, right? So therefore, in between each of these level, another level will be added in. By doing so, actually, if you look at it, whether you use a half VLSB or full VLSB, the quantization noise will reduce because there's a chance of moving to the nearer level. So therefore, the quantization noise will be lesser when you increase your N, right? So this is what it says here. If N increase, that means the resolution increase. So this is like the resolution of the ADC on the vertical sense. So if you increase 1 more bits, there will be 16 levels. So therefore, it become finer, right? Finer level. The steps become finer. So hence, the quantization error also gets smaller, right? So again, for digital resolution, front panel for digital resolution, here are basically the block diagram, and of course, there is the front panel and a block diagram, which is quite complicated. That's the reason why I don't require you to do it. But if you really want to do it, you can come, when you go to the class, you can come to me and request for the VI. I will pass it to you, right? But as for now, I will just demo to you what this all means. So basically, again, same thing. There is a A to C, and you are supposed to key in all the particular condition before you run the simulation and the observation. Now, of course, I would basically use that particular VI to demonstrate to you what is sampling rate and what is digitization resolution. So now I'm going to share with you the the simulation for using the VI. So now let me go to the simulation, the front panel. Now, if you look at here, again, let me hide the floating panel. You look at here, just focus on this portion here, the 3 tabs, simulated, offset, and outer filtering. This is a bit like what you have did in section 1 and 2. So you key in the frequency, you key in the amplitude, and key in the offset, and let's say your noise, what you key in. So after you run, I did a continuous run. So basically, this is an updated version. So you realize that if I define a sine wave with a 1 volt offset, this is not centering in 0 volt, but it's centering in 1 volt. So after a DC offset remover, I remove 1 volt of DC offset, you realize that now the centering is on to 0. If you look back here, this is from 3 to -1. So it's again 4 volt, but this is now from 2 to -2, again 4 volt, peak to peak, right? So therefore, this is with the DC remove. Then after that, you have, of course, if you add noise. So for example, I add noise here, right? You realize that it's very noisy, right? Then after the offset remover, the whole thing comes down, right? And then after the filtering, you realize that, hey, I'm actually quite good after removing the noise. Of course, this because I'm using a 2 volt amplitude and a 1 volt noise, so it's quite huge relatively for the noise compared to the amplitude. Now, if I change to a 10 volt, then you will see the drastic improvement. So if you look at here, 10 volt simulated, that's with noise, which is quite noisy. Then you look at it after the DC offset, and then of course after the filtering, you get pretty good sine wave. So that's how it means. Of course, I have centered my cutoff frequency at 16 Hertz, whereas the frequency of the signal is at 10 Hertz. The reason is because I want to do away with the -3 dB drop. If you put it at 10 Hertz as well, you realize that if I put this at 10 Hertz, you realize that my signal is actually only 0.7, about 7 volt instead of 10 volts, right? 7.07. So if I put it at 16, yeah, it is close to 10 volt. So therefore, I don't have an amplitude drop, right? So this is for the filtering, etc., etc. Now let's move to the lower portion, which we call it the sample and hold, right? So the white graph is denoting the filtered signal. That means after this filtering, which is this signal exactly. Now I just superimpose this guy here, and then there will be another red graph which is denoting what is the sample value. Now if I start to increase this sample value, pay attention to the red color curve. So as I move, you realize that there will be red color curve coming out. Now this is a distorted signal because there's still aliasing, right? So as I move, you realize that aliasing is still occurring and it's trying to make up to the final. So by taking enough sampling point, as I increase, the more I increase, the more it gets closer and closer to the final value, and eventually if you reach around, let's say I put 100, right, you can basically get a replica. So that's why it means, that's what it means, if you have enough sampling, that is looking at the X resolution, and it means in the X, how much I sample means that how close the resolution of this X point I will be able to replicate the signal, right? So that's for the X. Now next we are going to look at the Y side. Now Y side, of course, is controlled by your bit. So the number, of course, and a bit and a voltage range. Now if let's say currently I am using a simulated voltage of 10 volt, right? 10 volt peak to peak. Now 10 volt peak to peak, of course, you cannot be coded by 1.2 plus minus 1.2 volt, 25 volt range. And if you code it by plus minus 1.2 volt range, then end up your Y resolution is not enough, even though your X resolution of sampling of 100 hertz is enough. So therefore you cannot recreate the signal. So if you look at it here, the signal basically is a square wave because you don't have enough peak. Your maximum peak is saturating at 1.25 volt. Now if I just change the this guy here to 2.5 volt, that means plus minus 2.5. Again, it's not enough because this is a 10 volt case, right? 10 volt case, again, is still not enough, right? So you still have a square. Now, if I increase some more to 5 plus minus 5 volt, again, it's not enough because it has not reached the maximum yet. So again, if I increase to 10 volt, there you see it is almost there. That is the full range, right? So your top is at 10 volt minus 10 volt. So your full range is there. But of course, this is using a 4-bit. You realize that 4-bit, that will be 20 volt divided by 4 is 2 to the power of 4, which is 16 level. That means a 15 interval. So this is about 20 divided by 15, right? If you take a calculator and press 20 divided by 15, you will get 1.33 volt for the step size, right? So this is your 1.55 volt for the step size. Now, if I change this to an 8 volt, you realize that step size actually went down to 78 volts. And then, of course, the number of steps in between become higher. Now it's 2 to the power of 8. Right? 2 to the power of 8 is what? 2 to the power of 8 will give you 2 to the power of 8 will give you basically 256, and actually there is 255 level in between, and so on and so forth. So of course, if you increase it better, bigger, then again you would have smaller step size, and this by right should display much more dots, but I don't know why it's not displaying. But anyhow, the signal is enough, right? Let's stop and run again to see whether we can get it. No, we cannot get it. And likewise, if you go into 16 bits, again, you are going to reduce the step size to 0.3 millivolts. Okay, so with that, I'm going to stop the simulation. But before that, maybe I should show you a little bit on the block diagram of this block. So you look at it, the block diagram of this block looks something like that, right? So this is your first part, section 1 and section 2. Then of course, coming from here, this below here is created for section 3. Yeah. So it's also in your lab sheet. If you like to wire it out, you still may. So this is the part that is additional that you add in for this sample and hold, right? So with that, it comes to my end of the lesson. So remember to submit your section 1 and 2 based on the instructions. Section 1 for A to E, right? If I'm not wrong, and section 2 for the observation for A to C, right? So that's I need observation for section 1 and observation for section 2. Okay, how you do it, I have already shown you some example. How you do it, I leave it up to you. Now, the VI, I only need you to submit the VI for section 2. Section 1 VI, I don't need it. So please don't submit to me the section 1 VI. So basically, I need one document that contains Words document or PDF that contains section 1 and 2 observation. And then, of course, the VI you can submit directly, the VI that you use. Please take note that do not copy, and please be in time. You can discuss, but you do it yourself. That's the most preferred mode. Okay, if that basically that will be the briefing for the Lab 4 submission. I wish you all the best. Thank you and bye-bye.